Let's derive the magnetic field at a distance x from a long straight wire carrying a steady current I. We begin with a long straight conductor carrying a steady current I. Our goal is to determine the magnetic field at point P, a perpendicular distance x away.
The Biot-Savart Law is our tool of choice. It states that the magnetic field, dB, from a small current element, IDL, is proportional to the current, the length of the element, and the sine of the angle theta between the element and the line connecting it to point P, and inversely proportional to the square of the distance r.
Let's consider an infinitesimal current element, dl, along the conductor. The distance from this element to point P is r, and the angle it makes with the position vector is theta.
To proceed with the integration, we'll set up a coordinate system. Let the origin be the point on the conductor closest to P, so that dl is at a distance L from the origin.
From our right-angled triangle, we can express r in terms of x and L.
Next, we express sine theta using our coordinate system. From the geometry, sine of theta is the ratio of the opposite side, y, over the hypotenuse, r. Substituting our expression for r, we have sine theta in terms of x and L.
Now we substitute these expressions back into the Biot-Savart law. This gives us the magnetic field contribution from the element dl entirely in terms of L and the constant distance x. To find the total magnetic field at point P, we must integrate this expression over the entire length of the conductor, from negative infinity to positive infinity. This integral is best solved using a trigonometric substitution. Let's define a new angle, V, at point P.
From our triangle, we can see that L is equal to x times the tangent of phi.
Differentiating with respect to phi, we find that dl is equal to x times secant squared of phi d phi. Next, we substitute for L in the denominator. Using the trigonometric identity, 1 plus tangent squared equals secant squared, the denominator simplifies to x cubed times secant cubed of
all our substitutions in place, the integral transforms. The terms simplify beautifully, leaving us with a much simpler integral of cosine of phi. Integrating cosine of phi gives us sine of phi. Evaluating this from negative pi over 2 to positive pi over 2 yields a result of 2. This gives us our final, elegant result. The magnetic field B is equal to mu naught I over 2 pi x.
Let's analyze this result. The magnetic field is directly proportional to the current I and inversely proportional to the distance x from the conductor. The magnetic field decreases rapidly with increasing distance.